In this video, we're going to get into the proof of the soundness theorem. It is a very long proof that has 11 cases in the induction step, one for every derivation rule of SD. So we're not going to be able to do the whole proof in this video. I will do some of the more basic cases in this video and some of the more complicated ones in a future one, but we will set up the entire proof here. I'm not going to go over the methodology underlying the proof. I do give a big picture overview of the proof in a previous video, so I would recommend looking at that if you have questions about the kind of reasoning we're using here. All right, let's get started. The proof of the soundness theorem is a proof by induction on the number of lines in a derivation. We've talked about proofs by induction quite a bit in this class, but just remember that proofs by induction have three parts. First is a base case, and that's where you show that the claim you're proving holds for the most basic case of the thing you're doing an induction on. In this case, we're doing an induction on the number of lines in a derivation. And the simplest derivation, the shortest possible derivation, has one line, right? You can't have a derivation with 0 lines because there wouldn't be a derivation at all. So in our base case, we're going to prove that the soundness theorem holds when k equals 1, when you have a derivation with 1 line. Then we're going to set up the induction hypothesis, and just remember that that's when you assume that the claim you're proving holds for everything up until a certain point. And then in the induction step, you prove that, assuming that the claim holds for everything up until a certain point, it also has to hold for the next point. The reason why we have to do 11 cases in this proof is because we have to show no matter what derivation rule you're using to get to that next point, the soundness theorem is always going to hold for that next point. So that's why the induction step takes a little bit of time, because you have to go through each one of the derivation rules. Okay, so that's what the proof is going to look like. So I just want to start out by reminding everyone of what it is we're trying to prove. We're trying to prove the soundness theorem, which says the following. Given any set gamma of sentences of SL, and any sentence S of SL, if S is derivable from gamma, then gamma truth functionally entails S. Okay, so the soundness theorem is, again, making this very tight connection between these two claims about what makes an argument good. So we're going to prove that if S is derivable from a set of sentences gamma, then it must be the case that gamma truth functionally entails S. Let's get started with the base case. This is the first step of our proof by induction, in which we prove that the soundness theorem holds for the shortest possible derivation, a derivation of length 1. So length k equals 1. What does a derivation of length 1 look like in this case? Okay, well, it's going to have one line, and let's just say that the sentence there is S1, whatever sentence is associated with that line. So we want to prove that gamma 1 truth functionally entails S1, right? And that'll show that the soundness theorem holds in this base case. That's going to be quite easy to prove because S1 is an open assumption that lies in its own scope. So we know that S1 is going to be a member of gamma 1. Whoops, wrote that backwards. S1 is a member of gamma 1. In fact, we could say something stronger, that gamma 1 just is the set containing S1, but this is really all we need to show. So since S1 is a member of gamma 1, it's impossible for all the sentences of gamma 1 to be true and S to be false. It's impossible for all the sentences in gamma 1 to be true and S to be false. Sorry, S1 to be false. right? And that's because S1 is contained in gamma 1, right? So any truth assignment of gamma 1 that makes all the members of gamma 1 true must also make S1, which is one of the members of gamma 1, true. So we can conclude from this that gamma 1 truth functionally entails S1. Okay, that completes the base case. Now we move on to the induction hypothesis. And remember that whenever we make an induction hypothesis in a proof by induction, you want to assume that the claim you're trying to prove holds for everything up until a certain point. So we're going to assume that the induction hypothesis holds, we're going to assume that the soundness theorem holds for everything up until a certain point. So let's phrase it this way. Assume that, let's say, for every j that's less than or equal to k, if if you can derive sj from gamma j, then gamma j truth functionally entails sj. Okay, so this is just the soundness theorem restated so that we're hypothesizing that it holds for everything up until a certain point. And that's going to set us for our next step, in which we move on to the induction step. So in the induction step, now that you've assumed that the soundness theorem holds for everything up until a point, we want to prove that the soundness theorem is going to hold for the next point. So here's what we want to do in the induction step. Prove that if sk plus 1 is derivable from gamma k plus 1, then gamma k plus 1 truth functionally entails sk plus 1. Okay, so the connection between the induction hypothesis and the induction step is that the induction hypothesis assumes that the claim holds for everything up to and including k. And then in the induction step, we prove that the claim holds for k plus 1, so the next point in the series. Before we can go any further, I need to make a brief aside and just go over a couple of useful facts that we need to know in order to do the rest of the proof. So I'm going to label them useful fact 1 and useful fact 2. So whenever we appeal to these later on in the proof, we can just refer to them as UF1 and UF2. Okay, UF1 is as follows. If some set of sentences delta truth functionally entails S, and delta is a subset of gamma, then gamma truth functionally entails S. Okay, so this is a pretty intuitive claim. It's just saying that if S follows from some premises, delta, then it also follows from a bigger set of premises that contains all of the original ones. Okay, so gamma is either the exact same as delta, or it's a bigger set that contains all the same members as all the members that delta does. Right? So because gamma contains all the same members of delta, then gamma is also going to truth functionally entail S. Okay, that's useful fact 1 that we're going to be using quite frequently in the proof by induction that follows. Okay, useful fact 2 is the following. If gamma union Q truth functionally entails R, then gamma truth functionally entails if Q, then R. Okay, this one is perhaps a little less intuitive, but there is a proof of this in the textbook. I believe it's Metatheorem 6.3.3 in the textbook, and it follows very simply from some facts about the truth table of the material conditional. So I'll leave that to you to go back to the textbook to look over. Now that we have the 2 useful facts under our belt, it's time to go ahead and get started with the induction step. So we're going to prove in the induction step that the soundness theorem holds for any derivation of length k plus 1. The induction step is going to have 11 separate proofs, one for every derivation rule, and that's because we have to show that no matter which of the 11 rules you apply to get to line k plus 1, that the soundness theorem is still going to hold. In this video, I'm going to go over the proofs for two of the rules, two of the simpler ones, reiteration and conjunction introduction. And in the later video, we'll do some of the more complicated ones that involve subderivations. Even though some of the proofs are a little more complicated than others, they all involve the same three steps. The first step is to write out the format of the derivation using the rule of interest to justify line k plus 1. In this case, because we're going to start with reiteration, the rule of interest is going to be reiteration. So let me just write out step 1, and let's see exactly what that step is telling us to do. So I'm just going to write like a schema of what the derivation would look like. So here's line k plus 1. And we're using a reiteration to justify that line. So now we just fill in the blank. So let's say there's an earlier line j, and the sentence at j is sj. And at line k plus 1, we reiterate sj, and that's just going to be sk plus 1, right? So sj just is sk plus 1 because that's the sentence at line k plus 1. All right, so that's step 1. We wrote out the format of the derivation using the rule of interest to justify line k plus 1. Now it's time to apply the induction hypothesis. So remember that the induction hypothesis, we assumed that if you can derive sj from gamma j, then gamma j truth functionally entails sj for all j that's less than or equal to k. So basically, in order to apply the induction hypothesis, we need to get a claim of derivability, and then that allows us to get a claim about truth functional entailment. Line j here falls within the scope of the induction hypothesis, right? Because j is less than or equal to k, so although k plus 1 doesn't fall within the scope of the induction hypothesis, j does. So we can say the following about j. Sj is derivable from gamma j, where gamma j is the set of assumptions available at line j. Okay, and because Sj is derivable from gamma j, by the induction hypothesis, IH, I'll write that a little more clearly. Whoops, everything disappeared. By the induction hypothesis, abbreviated as IH, gamma j truth functionally entails Sj. Okay, so now we've applied the induction hypothesis. So that's what step 2 is, right? So we're done step 1 and we're done step 2. Now it's time to move on to step 3. This is where a little bit of creativity is required in order to ultimately get what we want in the proof. So depending on what problem you're dealing with, you'll either want to reason or use one of the two useful facts, or both of them that we talked about earlier in the video, to transform what we have into a statement about what sk plus 1 truth functionally entails. So remember, ultimately, the goal of this proof is to get to a statement that gamma k plus 1 truth functionally entails sk plus 1. All right, how are we going to do that? Well, in order to do that, we need to find a relationship between gamma j and gamma k plus 1, right? So we want to figure out how the set of assumptions available at line j is related to the set of assumptions available at line k plus 1. In this case, it's going to be exactly the same assumptions available at both lines because they're both on the same scope line. So here's what we might say. We might say that gamma j is a subset of gamma k plus 1. Right? Actually, they're going to be exactly the same set, so it's trivial that gamma j is a subset of gamma k plus 1. So I'll write gamma j is a subset of k plus 1 because all the same assumptions are available at both lines. Available at line j and line k plus 1. Okay, now recall useful fact 1. I'm going to write it up here. Okay, so useful fact 1 said that if delta truth functionally entails S, and delta is a subset of some larger set gamma, then gamma truth functionally entails S. Now we have the information we need in order to apply that, because we have here by the induction hypothesis that gamma j truth functionally entails Sj, and gamma j is a subset of gamma k plus 1. Okay, so we have these two first parts of the useful fact. So now we can conclude that gamma k plus 1 truth functionally entails Sj. Okay, so that was just an application of useful fact 1. So by useful fact 1, right, because gamma j truth functionally entails Sj, and gamma j is a subset of gamma k plus 1, gamma k plus 1 truth functionally entails Sj. Now there's only one more step we need in order to get to the conclusion we want. We just have to say that Sj is the same thing as Sk plus 1, right? Because we just reiterated Sj on line k plus 1. So we can conclude that gamma k plus 1 truth functionally entails Sk plus 1. Okay, so that completes the proof for reiteration. Again, it was just 3 steps. First, we wrote out the format of the derivation using the rule of interest, in this case reiteration, to justify line k plus 1. Right, so that's here. We justified line k plus 1 using R. I would actually put in the line justification there. Right, so it's reiteration of line j. In step 2, we applied the induction hypothesis, so we took a claim about derivability that fell within the scope of the induction hypothesis, and then changed that into a claim about truth functional entailment. Then, step 3, we used useful fact 1 to transform what we had into a statement about what gamma k plus 1 truth functionally entails. Sorry about that. Yeah, so we used it to transform what we had into a statement about what gamma k plus 1 truth functionally entails, and that's what we ended up with here. I'm going to do one more example in this video, and this is going to be the proof for conjunction introduction. So we're going to prove that if line k plus 1 is justified using conjunction introduction, that the soundness theorem will still hold. Step 1 is the same as before. So we're going to draw the format of the proof. I'll write out step 1, where k plus 1 is justified by the rule of interest. So here we have line k plus 1. Okay, and that's going to be justified by conjunction introduction, and we'll write out the line justification before that in a second. Okay, and now we're just going to fill in the rest of the what the derivation would look like. Okay, so let's say that there is an earlier line I with the sentence Si, and another earlier sentence J with the sentence line Sj, and at line k plus 1 we use conjunction introduction to bring them together. So line k plus 1 is going to be Si and Sj, and that's just going to be the same thing as Sk plus 1. And we justify that as J conjunction introduction. That completes step 1, so we wrote a schema of the derivation where line k plus 1 is justified using conjunction introduction. Now step 2. Okay, we want to apply the induction hypothesis. So we want to take claims of derivability about the earlier lines that aren't k plus 1 and transform those into claims about truth functional entailment. So what can we say about the derivability of S1 and of Sj? Well, we know that Si is derivable from gamma I. Sorry, I think I've been saying S1 instead of Si. I meant to say Si. So we know that Si is derivable from gamma I, and we also know that Sj is derivable from gamma j. Okay, so those are two derivability claims. And we can say now, by the induction hypothesis, we have the fact that gamma I truth functionally entails Si, and gamma j truth functionally entails Sj. Okay, So now we've applied the induction hypothesis. That completes step 2, right? We transform these claims about derivability of earlier lines that fall within the scope of the induction hypothesis into claims about truth functional entailment. Now it's time to use the useful facts in order to make a claim about what is truth functionally entailed by gamma k plus 1. So how are we going to do that? Well, again, I think useful fact 1 is going to be helpful, right? Because k plus 1, sk plus 1 falls within the same scope of S1 and Sj, we know that all the same assumptions that make Si derivable and Sj derivable are also going to make sk plus 1 derivable. So let's say this. Gamma I is a subset of gamma k plus 1. And we can say the same thing about gamma j. So gamma j is a subset of gamma k plus 1. Okay, so again, exactly the same as we did it in the reiteration proof, by useful fact 1, okay, because gamma I truth functionally entails Si, and gamma I is a subset of gamma k plus 1, we can conclude that gamma k plus 1 truth functionally entails Si. We can also say the same thing about gamma j. Because gamma j truth functionally entails Sj, and gamma j is a subset of gamma k plus 1, gamma k plus 1 truth functionally entails Sj. Okay, so now we have these two claims about what is about what is truth functionally entailed by gamma k plus 1. Right, we have the fact that gamma k plus 1 truth functionally entails Si, and the fact that gamma k plus 1 truth functionally entails Sj. So now what we can do is appeal to the truth table for the ampersand in order to say why Si and Sj is true at k plus 1. So by the truth table for ampersand, if gamma k plus 1 truth functionally entails Si, and gamma k plus 1 truth functionally entails Sj, then gamma k plus 1 truth functionally entails Si and Sj. Right? So a conjunction is true if and only if both of the conjuncts are true, and we've proved that both of the conjuncts are true at line k plus 1, so we can conclude that their conjunction is true at line k plus 1. Okay, so again, like last time, there's one final step, right? So we want our final line to be, so gamma k plus 1 truth functionally entails sk plus 1. And we have here that gamma k plus 1 truth functionally entails Si and Sj. And we know from our derivation schema from earlier that Si and Sj just is sk plus 1. Okay. So now we can conclude that gamma k plus 1 truth functionally entails sk plus 1. And that was the whole proof. Again, so it was just 3 steps. First, we wrote out the schema of the derivation using the rule of interest, in this case, conjunction introduction, in order to justify line k plus 1. Then we here applied the induction hypothesis, right? So we took claims about derivability of sentences that fell within the scope of the induction hypothesis and transformed those into claims about truth functional entailment. In the third step, we used the useful fact, right, to make a claim about what gamma k plus 1 truth functionally entails. And that completes the proof. So it's very similar reasoning in each of the cases, even though some of the justification is a little different.